Well, I want to thank the organizers very much for the opportunity to speak here today. In Brian's metaphor as a sociologist, I guess I'm the spoonful of sugar in this morning's cake. This is really a timely conference. At a meeting I organized earlier this summer for scholars in the emerging field called diverse intelligences, one of our plenary discussions turned to the topic of science communication. And one of the senior scientists remarked that the real issue these days was that the public doesn't know how science really works. It doesn't see science as a distinctly human and distinctly fragile achievement. The old public ideology of science imagined scientists as solitary, disinterested seekers of truth, maybe a collection of iconoclastic geniuses. But these pictures, in their partiality, open the door to other images. The scientist is a figure corrupted by social or cultural forces, and this, true, has some partial truth. But I want to present a different way of thinking about science and scientists, one that draws on both the new sociology of science and complex systems, a view that emerges when we turn the lens of science upon itself. And that's to think of scientists like this ant. She has limited cognitive capacities and behaviors, but by her interactions with other ants, with their pheromone trails, with their collectively built environment, she and her sisters can do marvelous things. So I don't think of scientists as intrinsically special, much as that may hurt our self-image. We're ordinary humans, embedded in certain social and technical contexts, drawing on certain interaction rules, and equipped by certain training procedures. And because of this, we can do amazing things too. The story I'm suggesting that we should tell about science is that science is a complex socio-technical system for collective knowledge making, where complex system just means a system with heterogeneous parts that strongly interact and exhibits emergent behavior that can be hard to predict. I want to fight against and challenge the assumption that you sometimes see when scientists talk about science, that the social parts of science are what are responsible for bad things happening, and in fact to argue that the social part of science is essential to how science works. And this is what I mean when I talk about the social production of knowledge. Science as an institution, a social arrangement that produces the people, the things, and the interactions that allow collective knowledge to be created. This is an integrated relational view of science as part of the larger emergence of intelligences on our planet. And I view science as an information processing problem, a problem of learning. So how can we think about science in this way as a kind of collective computation? First, I'm going to draw on some examples from earlier work in the study of biomedicine and draw out some of the core algorithms and protocols that allow scientists to become collectively intelligent, respecting the hardware, so to speak, that is, the humans that actually have to do science. And to do this, I'll use one exemplary problem that this collective intelligence has to solve, the organization of attention, while also highlighting the way in which the solution to that problem can lead to a kind of perilous outcome of getting stuck. And then I'll turn to a formal analysis of institutions, focusing in particular on the kind of looming problem of unintended consequences. If science really is a kind of social complex system for learning about the world through socially producing collective knowledge, we need to think very carefully about pulling on policy levers, about the intelligent design, if you will, of this cultural technology. And then, if all goes well, I will tie it up in a bow with some theoretical musings on the social foundations of collective knowledge making in science, plus a very speculative discussion about the consequences of AI on the evolution of scientific knowledge. So let's turn first to our empirical example, how scientists choose what problems that we get to know. Questions are, of course, asked in a rich social and technical ecology, and if you want to get in the kind of technical and methodological details, you can check out this paper in American Sociological Review with James Evans, who'll be talking later today, or later this week, and Andrei Reshetsky. So what kind of processes affect where an exemplary scientist directs her research attention? Her past interests and her training, of course, and these are also the outcome of social processes that impose their own limits on the kinds of questions she asks. But I want to argue that she also attends to her overall reputation in the eyes of her colleagues, her standing in the scientific field to use the term for the French sociologist Pierre Bourdieu. And it's this reputation that allows her to make further claims and have them be taken seriously. So there's this kind of cycle where scientists make research claims. Based on that claim, she experiences some return in capital, and that may increase her reputation, move her up in this space of positions. Now note that caring about this sort of thing is a necessity, even if she truly is purely, quote unquote, motivated to seek the truth. In order to do that in the scientific institution, you have to stay in the game, and this is part of staying in the game. And one of the things that I'll argue is that science is leveraging, tuning, and refining more fundamental, learned, or innate human tendencies, some of the things that Melissa talked about earlier, things that are manifested in many different fields, like attending to status and position, and attending to the past choices of others. These help organize scientific attention. Now, one of the biggest distinctions in this space of research claims is between moves that further cluster attention, that is, follow tradition, and those that strike out into new territory. I think you can get which of those is which. Clustering attention leads to productivity. It's predictable. It's also kind of boring. Striking out into your own can lead to revolutions, but it's quite risky. You're kind of hanging out there by yourself. So call the first tradition, the second innovation. To analyze this empirically, we make the fundamental assumption, and I'm glad that Dean introduced this point of view this morning, an explicitly combinatorial view of discovery where we take a time-ordered sequence of millions of documents, in this case about biomedicine broadly construed, and turn them into evolving networks of chemical knowledge, and then we have a way to map the structure of that network onto these different categories. And the first takeaway is that a huge amount of this involves following the herd. So we find that attention is very organized. In fact, this basic organization is quite stable over a multi-decade period that we study. And this is surprising because this is the combinatorial explosion issue that was mentioned this morning. The pasture has, in the same time, gotten vastly bigger. There are more opportunities to innovate, to make new connections. And yet, biomedical scientists, by and large, remain clustered in a safe corner. In fact, there seems to be a kind of herding heuristic at play here, one that's in tension with a propensity to strike out for the new. And in the paper, we infer the kind of strength of these focusing processes that direct attention on tradition. What helps to shape and sustain these dispositions? How are they socially produced? Well, one of the things that helps to sustain them is this reward process. And I want you to think for a moment about two important reputation mechanisms. One is citations, one of the nice ways that we can quantify the currency of science. Brian mentioned this morning, by the way, the strangeness of economists. And so here's a great illustration of socialization into caring about things. There is a paper in 2013 that looked at basically how much of a body an economist would sacrifice in order to publish in American Economic Review, which is the top journal in their field, and it is more than half a thumb. So this is part of the socialization process to turn people into beings who think that that's a fair shake. And there's the citation if you want to check it out. Now, what we find is that in terms of this currency, more innovative moves are indeed rewarded more highly. And then this raises this question: is innovation a rational way to obtain citations? If that's all you cared about is producing papers, accumulating citations, is this a rational way to pursue that goal? And in order to answer that question, you need to ask yourself, how much riskier is innovation than tradition? Is it twice as risky to combine things that have never been combined before? Is it 10 times as risky? Well, it turns out in order to be indifferent in terms of the expected reward, combining things that have never been combined before need to be only 24% more risky. Adding a thing that has never been studied before, 35% more risky. We all know that trying something new, making a new combination, this is, by the way, a great illustration of the combinatorial nature of inventions, sometimes being very visible, it's much more likely to fail than that. So tradition, from that perspective, is the best strategy for reliable citation accumulation. So what explains innovation? Well, partially this is a hero story issue. Consider big rewards. When we look at 137 different prizes, focused especially on elite prizes like the Nobel and very high-tier citations, we find that that research output is indeed enriched in some of these innovative risk-taking moves. So on the one hand, under our current institutional arrangements, this herding heuristic is adapted to accumulating citations to kind of stay in the game. And that helps to organize scientific attention around zones of tradition. But it's in tension with another, imitate successful scientists, imitate the heroes, which is again institutionally sustained by things like prize giving and of course baked into scientific pedagogy. So this is a case where there's a kind of socially produced limit through the ways in which the basic affordances of the human hardware, like striving for recognition or status, are used to implement a kind of collective discovery algorithm. Now, how do these kind of limiting processes add up? To answer this question, there's a kind of companion piece that came out in PNAS where we look at how scientists attend not just to this kind of tradition-innovation dichotomy, but rather, among other things, the kind of combinatorial properties, the previous choices that others have made in looking at chemical entities. We also look at the distance between them as a kind of proxy of cognitive distance with a network, very similar to what you heard in the first session this morning. There's a complicated generative model. We figure out the parameters that are kind of the best explanation for the data, and what we find is that the kind of modal strategy is a very conservative one. It's where you connect an important chemical, one with high degree, to a less important one, ideally quite close together in the network. And we know that this kind of local discovery algorithm is pretty rational, given a proper understanding of scientists' institutional ecology. It limits their own horizons, but what happens to science as a collectivity? Does this distributed algorithm serve the goals of science, or does it impose collective limits? And in order to explore those collective consequences, what we had to do is take a sample network, a kind of smaller proxy, because it turned out this was very computationally expensive to do, and simulate the exploration of that network over and over and over again, changing the discovery algorithm to see if we can do better than the kind of modal one that we discover from the data. It's kind of like running the tape of scientific history over and over again under different kinds of institutions. And what we find in terms of efficiency, where this is just measured in terms of the number of experiments that you need to do to discover a certain amount of the network, is that the modal strategy, the one we learned from the data, does a good job discovering some initial islands of knowledge, but it performs pretty poorly later on, filling out the rest of this network. And to kind of visualize this, this is a planar network where that same discovery algorithm that we learned from the data is implemented, and you can see it kind of creates these islands of knowledge in a vast, sea of ignorance. We find, of course, other strategies, riskier strategies that do much better, but remember, these strategies have to be implemented, at least right now, on human hardware under existing institutions, and they generally involve engaging considerable risk, including risk that we need to get society, individual scientists, funders, those sorts of things to accept. And that's something that can be quite challenging, but there are ways to kind of get beyond this socially produced limit. For example, you can provide explicit incentives for more radical behavior. HHMI does this by providing longer-term funding for people rather than projects. One of my favorite examples is the Grand Challenges approach that the Gates Foundation carried out. Andrew Saracen was involved with this at the time. He's now at TWCF. And this approach explicitly selects for potential impact and innovation using a kind of champion-based peer review process that tries to pick out those really innovative, risky moves. But another institutional response might be to change the standard response to failure. So an experiment fails. What do we normally do? It goes into the garbage bin. It is publication bias, and this can have some unintended consequences. One of the things that we try to do is see what happens if you coordinate research more. If you, for example, say, everyone discloses the result of an experiment, whether it worked or not, and then moves on. And it turns out that under this kind of institution, for some objective functions, that is rapid discovery, coordination makes discovery much more efficient. In fact, the Medline strategy plus this coordination can be almost as efficient as these more optimal, very risky strategies that we've discovered. And this illustrates something really interesting and important about these kind of socially produced limits on scientific knowledge. They can be broken by institutional change. And not too far from here in 1992, Oliver Selfridge, in talking about collective intelligence, emphasized building in both change and changes in the rule for change. And I think one of the things we're all trying to do here in Metascience is think about changing the rules of change for science. But let's think more deeply about changing those rules, and in particular, dig into the perils of institutional design and the constant specter of unintended consequences that haunts them. This, I think, is a great example of why we need both empirical work, these kinds of experiments in changing review processes, et cetera, but also some theory building, because I'm going to show you a little theoretical model that turns out to produce an interesting, very surprising unintended consequence. This is some work with Carl Bergstrom and Darcy Song in a sort of enterprise using tools from game theory to try to model aspects of science. Here these guys are. Carl is here and will also be talking later this week. You can read the paper up on the archive. And the mental model here, again, is one in which scientists make research claims, get some return, and they care about these sorts of things. There's a great term called epistemically sullied, basically saying, oh, scientists care about things like rewards. So given that they do care about these things, how does that lead them to allocate research effort across problems? I should say, by the way, some of these slides you'll note are exceptionally beautiful, and I have to thank Carl for the baseline of those slides, which I have tweaked and probably made much worse. So the kinds of questions that we're interested in are what we call big problems. Things like, say, the Lamb shift. If you don't know what this was an empirical finding that there was an unexpected energy difference in two of the energy levels of the hydrogen atom. That turned out to be an important motivator for the development of quantum electrodynamics. And these big problems have a bunch of characteristic properties. They're well-defined in their scope. The community agrees they're important. It's more rewarding to solve them than kind of day-to-day work, but it's not a grind. In other words, it's not just throw resources at the problem, and whoever throws the most resources is guaranteed to grind it out and solve it. It may require some kind of insight. It can be useful to society at large, but it need not be. And importantly, it pulls scientists away from what they're doing otherwise. So to model this, we adapt a tool from economics called a patent race and set up something we call the credit race. So imagine continuous time, you have n scientists, and those scientists have their ordinary work that they do. Then this problem pops up, and they have to decide, do I work on the problem leaving behind my ordinary work, or do I stick to what I normally do, to my outside option? It's a continuous time setting. The first scientist to solve the problem gets all the credit. Everyone else who's working on the problem gets 0. And scientists are epistemically sullied. They aim to maximize the credit they receive. They also vary in their endowment of scientific capital, what they can bring to bear on the problem. Now, this affects both the rate at which their outside option pays off in credit, but it also affects their probability of solving the problem. It doesn't affect the startup cost. We assume everyone has to pay a fixed startup cost. But the instantaneous probability of solving the problem is proportional to your scientific capital and inversely proportional to the problem's difficulty. So this leads to a distribution of the time to solution. In particular, it leads any particular scientist's probability of winning the race to just be how much of the total endowment of scientific capital thrown at the problem she accounts for. And if she solves the problem, she gets a payoff of V, everyone else gets 0. Incidentally, these kinds of models are often used to model insight problems, ones that involve a kind of eureka moment. Now, what we assume scientists want to do is maximize this utility. And in this case, they're going to jump in anytime this is positive. You can break this up into parts that all make sense. Reward times chance of winning, minus opportunity cost times the amount of time you're expected to pay that cost, minus the cost of entry. And what happens? Are you ready to be astonished? Well, individuals with highest scientific capital pursue the problem, everyone else opts out. I know. And that's a problem with models. It's easy to get them to do what you expect. What's more interesting is when you're surprised. And so I want to tell you now about an extension we made to this model where we were quite surprised. And that's to do something we know happens in science, publishing partial results. Under this tweak of the model, the problem now comes in stages. Anytime you publish a partial result under this institution where you're allowed to do so, you get credit for solving that stage, and everyone can start at that point. So in this example, green scientist reaches the solution to stage 1, publishes, everyone gets to start there. Stage 2 is reached by the purple scientist. She does not publish, keeps going, solves stage 3, and gets those 2 bits of credit. This is, of course, part of the institution of ordinary science. And under this setup, it's reasonable and very straightforward to show that if this institution where you can publish partial results is present, scientists will indeed publish intermediate results under quite general conditions. But is this institution always a good thing? If you ask yourself that question, I think you'll find your standard mental model of science, which is standing on the shoulders of giants, right? It says, yes, this allows knowledge to accumulate easily. But that's not what we find. Allowing partial progress sharing does not necessarily accelerate the rate at which problems are solved. And what's going on is in your mental model, you're implicitly assuming essentially that scientists are forced to work on the problem. We don't explicitly state that, but when you think about why that heuristic played through, you're holding the set of participants constant. And if that's the case, of course, partial progress sharing accelerates time to solution. But in fact, working on the problem is strategic. And so when the rules of the game are changed so you can opt in and opt out, under that institution, scientists can drop out from harder stages of the problem, work on their normal work, and that ends up extending the overall time to solution. Now, we were very surprised by this finding. It was very delightful. And then later found a beautiful experiment using coding competitions where they changed exactly this kind of institutional factor, and they find indeed results that are consistent with this prediction, which is a great illustration of the way that our mental models can be wrong. Now, to wrap things up, I want to take a little step towards providing a more kind of formal computational theory of science's collective computation, something that connects to some of the themes from earlier this morning. If you want to read more details of this, there's a paper last year in Poetics where I used science as a kind of running example to develop this. And the learning model is something called PAC learning, or probably approximately correct learning, developed by the computer science Leslie Valiant. And the basic structure of this model is that individual learners have some set of features they can detect, and then some stream of experiences that confront them. So there is some algorithm for converting experiences into new features. So these regularities in the stream of experience are transformed into what you might call classifiers that recognize them. Those in turn allow you to recognize more regularities and build more classifiers, and so on and so forth. Now, under this picture, immediately we can sort of think more clearly about a lot of features of science. For example, an important first step is to constrain the stream of experience so the features are more limited. The regularities are easier to learn. And then we may try to generalize what we've learned in that stream to some other stream. In cases where we're sure that everyone has similar streams of experience and we're recognizing the same regularities, well, that's replication. When we're confident that the streams are different, but the same thing works in multiple streams, that's robustness. Now, one of the things to note is that, as we are all sadly aware, we have finite amounts of time and finite amounts of cognitive energy. Yet what scientists need to know to do science is not just growing, it's layering one on top of the other. So how can science be cumulative? I mean, look at all the things you have to understand in order to be a high-energy theorist these days. You have to know about Yang-Mills theory, plasma, quantum chromodynamics, et cetera. This is an abstract, incidentally, right? So one way to do that is to make this process more efficient, and that's, of course, pedagogy. Pedagogy is the art of presenting examples so concepts can be learned more rapidly, and proper pedagogy is essential to socially producing knowledge in science. It's the social production of persons who have similar and compatible repertoires of scientific classification and action. Also a similar feel for the scientific game. So now we can look at how that model helps us to understand things like the production of consensus and the maintenance of tradition. This is equipping people with similar focus of their stream of experience, similar repertoires of recognizing regularities in that stream of experience, and similar manipulations. It also helps us to think about simultaneous discovery. When it happens that there are lots of folks who have similar streams of focused experience and similar classifiers, it's not surprising that they might come up with the same regularities at the same time. It helps us think about teams as a way to expand the set of regularities that can be recognized more cheaply. It even helps us social scientists feel a little better about why what we do is so hard. The regularities of the social world are just difficult to learn. They're complex, they're context dependent, they tend to be kind of disjunctive concepts, and they change on rapid timescales relative to what we learn and because of what we've learned about the world through reactivity. So we can feel a little bit better about how hard social science is to do. Now, I want to just mention very quickly, since Paul Thagard has come up once today already, that there's a beautiful book, which I would encourage you all to look at, called Induction, that presents a kind of early combination of genetic algorithms and a connectionist model, something called a classifier system, that can help us think about how the social organization of science supports the learning of robust regularities about the natural world. And that's basically that there's a map between this classifier system picture and the picture that I advanced when I was telling you about this Bourdieusian field theoretic model. Why this kind of social organization works in this way? Well, I want to suggest that there's a connection between these two things. So let me just rehearse fields again. Scientists compete to make claims about the world. They desire and receive recognition of their peers, scientific capital, when they succeed. That allows them to make yet more claims and have those claims be taken seriously. Occasionally, they get strong validation. Credit flows both to them and to the folks that they've cited, allowing yet more claims to be made, and so forth. The classifier system picture with a credit assignment algorithm called the bucket brigade basically works like this. Classifiers compete to represent the environment, they accumulate strength, they make claims on the basis of that strength, and then when those claims work out, they get paid in credit. So I want to suggest that the field provides a setting wherein the social goals of scientists, to which their dispositions are adapted by socialization, in the field structure, their social goals serve the cognitive goals of science as an institution. This is a way in which the social becomes essential. So I want to close very quickly by talking super speculatively about the future. And that is to raise a scenario that you will be familiar with if you have read Douglas Adams' book at all. This is what I call the road to 42. As you may know, 42 is the answer that deep thought presents to the question of the life, the universe, and everything. And it turns out that the problem is that you don't know what question is really being answered, and once you know what that question is, you understand what the answer means. So let me suggest just a toy model for the use of machines in science. Not super intelligence or anything like that, just a human brain equivalent, but cheaper to build and run than an actual living human being. If you recall from our earlier model of credit races, let's focus on this term, the expected duration, and note that in the denominator is the total scientific capital thrown at a problem. If all human scientists have the same scientific capital, then if you have n scientists, that's n times h. Now assume that these human brain equivalent scientific AI increase the number of brain equivalents by a factor of m. So now we have m times n times h thrown at the problem. It's straightforward to see the expected time to solution now has this 1 over m factor. Depending on how big that factor is, in that case, the time to solution might get very, very small. In one scenario, this creates a crisis of management. Basically, these human brain equivalent AIs can't set their own goal, but the timescales of asking questions, knowing the answers, deciding what to do next, those change much more quickly relative to typical experience. The second and more challenging scenario is what I call a crisis of understanding. In that case, these machine intelligences can set their own goals, and that means the timescales of asking the questions, knowing the answers, and understanding what it means change radical to our typical experience. Now, the first can be quasi-solved by essentially devoting some of this to, I will complete my thought, to middle management. The more challenging scenario in which there's a crisis of understanding really ultimately demands pedagogy. Because, and you can sort of show that if we say don't know what differential equations are, Newton's laws are very hard to state or understand, you can quickly arrive at a situation where the regularities that are being learned about the world are completely illegible to us. And this creates an interesting research opportunity for trying to understand how machines can not just have explainable answers, but can actually teach us those answers, how we might communicate with them. There's a beautiful theoretical computer science literature on this, which I'm obsessed with currently. But my time is up, so I want to say 3 things. One is to make a brief plug for the Diverse Intelligences Summer Institute. If you're an early career scientist who's interested in questions about metascience and whatever, please apply to come. We also have a postdoc position available, so I know there's some great talent in the room for that. I want to thank the folks who supported the work. I want to thank you for your organized attention, and most of all, for your work that has made science better and will make it better in the future. So, okay, thanks.
So if I may start, there's
yes,
no alternative on the other side this time.
That makes it an easy choice.
I fully agree with you that science is a social activity. I think it's self-evident. But what it implies is that if there's a problem in science as an activity, we have to look at a problem in a society, a scientific society, and a larger society. So since there are problems in science that we came here to discuss, including this irreproducibility problem, the first question is, what do you see as a societal problem that can explain what is happening in science, right? First, and second question is, my impression, I'm new to those fields, and I just saw a movie about Bourdieu, that's about it. But in general, what I have this impression that scientists, when they're considered as, subjects to all those equations, are considered as rational players, like economists do. And we all know what happens with economists' ability to predict recessions when they start, with the end, and all those disasters that come from considering a human being as a rational being. I'm not irrational, I know this about myself. So what do you think about how do they affect all your conclusions and conclusions of others if we just assume, I would say almost the fact, that scientists are not rational?
So those are both great questions. I am glad that you think it's self-evident that science is a social process, because I think not everyone.
I should say I'm not funding social research.
No, it's fine. Let me start with the second question. So I think one has to be transparent about the assumptions that are being made when using these kinds of models. That said, there are a couple of different ways in which you can appeal to more realistic models of, say, learning how to play equilibrium strategies that are more realistic learning dynamics than just inferring what the equilibrium strategy is and playing it. And in many cases, those kinds of dynamics lead to the same equilibria. So that's one of the things that can rescue at least some of these kinds of results from the evident fact that scientists are not purely rational calculating beings. The other point, which are one of my former colleagues, John Levy Martin, makes, is that there are cases where making the assumption of rationality can lead to pretty good inferences about behavior. And that's when what is changing is fundamentally the cost of some action or the cost of some behavior. And in those kinds of settings, holding everything else constant, it turns out to be you don't lose as much by making the rationality assumption. And so, I think arguably you can view some of the settings in which these kinds of models have been deployed as ones that involve modulation of cost. Let me very quickly answer your first question.
I mean, if I can comment on the second, because the thing is, the problem with this approach is, if you apply it in practice, what it would imply, you would select for rational players, for people who do research for rational reasons. And as we learned from the previous talk, these are not entirely compatible with what we know about people who do breakthroughs. So then this could be an explanation of what is happening, that taking this, simplifying it to this reductionist kind of simplified view of how science works can lead, is like feeding back into producing institutions that would encourage this type of work.
Sure, and so I mean, there is this phenomenon whereby institutions mold people's behavior to be more conformant with those expectations.
Okay.
I think that is part of what you might want to do in making those institutions effective in producing the kind of collective behavior you might want. So that can be both a feature and a bug. But you will note that I talked about both theory and empirics. And I'm not suggesting that you use this model to then say, okay, there are funders in the room, go out and fund in this way. I think it's much more useful for saying, here is an interesting unintended consequence that using your mental model of behavior might not anticipate. And when you do experiments like this Boudreau and Lacan experiment, you end up getting something that this theoretical model would predict. So I would say a much more sane use of these models is to explore possibilities and suggest things to test experimentally. Like at the end of the day, real human behavior has to be the judge, and that's why I think theory and empirics are both important in this case. Let's talk about your very interesting first question at lunch, because I want to give the folks over here a chance. Yes?
Thanks so much. I have a question about where we get explanatory power from when we consider ourselves as social and embedded in a society. So right now, obviously, 4S is happening in New Orleans, right? That's the Society for the Social Studies of Science. And obviously, they have a lot of overlap with the type of work we're doing here, right? They want to understand where explanatory power comes from. They want to know about the history of claims in science. They want to know about how to make institutions that could persuade the public to do one thing or another, all that stuff. I guess I wonder where work like this matches or interfaces with the work of like archivists or ethnographers, anthropologists, STS scholars, historians of science, who are actually going to take this model overall and then localize it to a particular period or particular conflict, and how we can get some crosstalk between those two, because this is really incredible. It obviously will convince a room like this. It'll play differently at a place like 4S. The 4S explanations will play differently here, but we're all interested in the same thing.
Yes. So I promise I did not plant this question, but that's such a beautiful question, and I'm very pleased you ask it. One of the things I think it's really important to do is bring the sort of science of science community and the science studies community together. I view a lot of the work that I do as, and if you look at the papers, often there's like, let's take this idea from Latour and try to figure out how to operationalize it so that we can test it quantitatively at scale. I think that's incredibly important. I actually learn just as much, maybe more, from talking with ethnographers and folks who do qualitative work, because ultimately what I'm really interested in is the texture of experience and the way that that aggregates up to produce these interesting social structures. And that's something that, until we get to the era of everyone being totally instrumented at all times and recording everyone's behavior always, is going to be illegible to, or very hard to translate into the kinds of computational or formal modeling work that I've talked about. So I think that's a really essential conversation to happen.
To follow up, but you're not discouraged that there's some sort of fundamental tension between like the positivist modeling, this kind of behavioral economics, and the type of like very relativist, very historical, very localized and kind of deep description, rich description of an interaction that they do. Do you think that's...
I am a pragmatist.
Yeah.
It's like, do what, try things, see what works, see what is in conversation with one another, even if the underlying pictures are quite different. Well, you have to make assumptions to do any kind of work. And that's grist for the mill from my perspective. So I think let's bring everyone together and let the sparks fly. They can throw heat and light. No. Yes.
So I have a question about the part of your talk when you discussed this model where we're trying to understand all the important problems. Find out all the important problems in the universe, and then we only discover part of the network. And you said one solution would be to publish everything, because then you can cover more parts of the network, or find areas within the network that are not covered. And so this gets at the core of this kind of debate about pre-registration,
Yes.
Open science, basically publish everything, make every study available, and creates potentially a world in which we discover more spaces, but also comes with costs, right? There's now millions of studies on completely worthless experiments being, published in, pre-registered and published. People throw thousands of subjects on uninteresting experiments and run studies using their undergraduates on problems that nobody cares about. So there are enormous costs with this kind of, let's publish everything, let's do everything. So have you tried to model these costs? Because these costs are actually, from a perspective of a working scientist, quite high. And we really don't want to live in the world where we stop making subjective judgment. Is it worth publishing? Is it not worth publishing? As a journal editor, you have to make these judgments about innovation and creativity and novelty, whatever the three things were.
So let me push back a little bit and actually say that I think in many cases, this would reduce wasted experimental cost or theoretical labor for the following reason. So how much wasted effort is involved this actually is both an efficiency question and actually an equity question. So imagine how much work is wasted testing hypotheses that seem very plausible, like the things that a lot of work is likely to get concentrated on and wasted are testing things that seems like it should work and turns out not to work. Now, how do you know not to test some hypothesis that has not been published with a negative result, but nonetheless, networks? Your friend says, oh, you're maybe trying to look at this thing. Well, we looked at that. It turns out there's nothing there, blah, 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 blah. So because we know that there is this kind of stratified organization of scientific social networks, that means that, to some extent, subject to constraints on the resources that are required to do those sorts of experiments, a lot of the wasted work may be being done by folks who just haven't heard the news yet. And so I totally agree with you that, among other things, you need to figure out how much waste is involved testing the same thing repeatedly versus testing trivial things. I think it's a very interesting modeling question. My suspicion would be that the sort of correctly designed institutional arrangements where, let's say, negative findings are pretty quick to put out and are essentially there for archival documentary purposes and maybe are accorded much lower credit for that reason, where that's a kind of minimal cost thing and where higher scientific effort is associated with these things where it is an interesting positive or determining negative finding. So yeah, that's how it. Do we? Or are you going to ask a question?
Let's.
Okay, great. Okay, thank you all.